So first of all, I would like to explain a bit what is this idea of persistence. And in fact, it comes from physics, from the physics literature. So one of the first examples is the one, so you can see the picture here. So take a surface, and at time 0, let's say that this surface is totally dry. And then we have very small droplets of water which come into that surface. And the question is to compute the probability at time t that if you fix a small portion of the surface, so for example, a small disk here, this portion will be empty of water. So it's a very concrete question in physics. And it has been shown that, so this is called a persistence event because it is a probability that something weird, rare, let's say, will happen. And it can be shown that this probability will decay to 0 in some way, which is interesting in physics. And so we can compute how fast this probability will go to 0. And so on this slide, I have taken a few other examples from physics where we are interested in persistence problems. And another one is this Ising model. So we all know this famous model from physics. So in dimension 1, you can imagine a line. So let's say Z, and you have infinitely many spins, and the spins are directed up or down, I mean, as classical in the Ising model. And again, you can look at some proportion of the spins, and you can compute the probability that these spins don't move in some dynamic Ising model between time 0 and t. And if you compute this probability, or how fast it will decay to 0, again, you are interested in some persistence probability. Now I move a bit to random walks. So maybe you can take a look at the picture at the bottom of the slide. So we have here a kind of slope. I mean, it's just a random walk, and it will give, so it's a bit like some environments. And if we're in a valley here, it makes that the particle, it's quite hard for the particle to go up. And on the contrary, if you are here, it will be very easy for the particle to go down. And if you look at this model, called sometimes a CNRS model, there is a typical question, which is to compute the probability to stay in some valley. So for example, in this one here. And we know that it will be somehow exponential time. And the question is to quantify exactly this persistence event to stay in some fixed domain when time goes to infinity. So you see there are many different events and examples where we can compute and define a persistence event. So maybe I can close my list of examples by another very concrete example related to plate tectonics and to earthquakes. So again, you can take a look at these two pictures here. So the first one shows a kind of profile of environments. And in fact, some physicists did experiments showing that if you want to compute in some earthquake how fast you are going to have a propagation of the earthquake, not how fast, but how long, I mean, what will be the distance of propagation, it's proportional to, it's a persistence event, in fact, and it's proportional to the integral of this landscape here. And so as you can see, if you are able to compute this persistence event, you will be able to say how long, what will be the typical distance of propagation of some earthquake. So yeah, just to say that we have many examples from physics where we want to compute a persistence event. And now I move to probability. We also have a lot of nice and very famous examples of persistence events. Maybe the first one is the most famous one. It's called the ballot problem. So it's a picture on the right. In this example, we have two candidates, A and B, and we have a vote between the two candidates. So at time 0, we have a 0 vote, like here. And if the candidate A has a vote, then we move to the right. And if candidate B has a vote, we move to the north, so up. And so if you look at this red path, then you have, it describes the votes of this problem. So in this example, what happens is that the candidate A has always more votes than the candidate B, because we are in this lower part of the quarter plane. And it's exactly what is this ballot problem about, is to compute the probability that candidate A has always more votes than the candidate B in the count of the votes. So it's a classical problem, and hundreds of years ago, people were able to solve this problem, and there is a very simple formula to compute this probability. So it's just one example of random walks, but in fact, there are many. Every time you have a random walk in dimension D, you will get similar problems. You can define any kind of domain in ZD or RD, and a persistence event will be the probability that the walk stay in some domain when the time goes from 0 to some fixed n. So it's related to what we call fluctuation theory of random walks, and we know that we can compute first passage times or survival probabilities. So this can be interpreted as a persistence event. And to say something about my research, so I was quite interested in the last years about processes in cones, as Rafik was kind enough to say. And again, it's related to persistence because we have cones and we want to locate the random walk in a cone, so something we want to compute. And if you like, yeah, so all these examples in fact are discrete random walks, but of course we also have diffusions. And if we have continuous processes, we have exactly the same questions. And one famous subclass of diffusions is given by Gaussian processes like Brownian motion. And in all books, classical books about stochastic calculus, we have beautiful formulas for example, Brownian motion between two lines or this kind of probabilities related to special functions. And again, we can say that this is persistence probabilities. Okay, so it was just a very small recap about classical examples in probability and physics. And in fact, many of these problems will be quite difficult to solve. So if we're able to say something just asymptotically, let's say some probability P of n will be equal to asymptotically to n to the minus alpha, we'll be already happy. Okay, because I mean the problem is difficult, so we just want to have an approximation of the probability. So sometimes it will go to 0 polynomially fast, like this, and some other times maybe exponentially fast. And in any case, so we call this alpha the exponent, the persistence exponent of the model. Okay, so to continue, I need to state a very beautiful result called the Spar-Andersen theorem. So I state it in dimension 1, but there are multi-dimensional versions of this theorem. So take a random walk in Z. So just a sum of n variables which are independent and identically distributed. And for me, in this talk, a persistence event will be this probability. So it is a probability that if you look at your random walk, it will stay non-negative between time 1 and time n. So just one example of persistence, but for me it will be the definition of a persistence probability today. So in the slide before, I was mentioning the first passage time. So if you define tau to be the first time that the process becomes strictly negative, it's equivalent to say that you are non-negative between time 0 and 1, or to say that the first time you become strictly negative will happen after time n. So it's just a reformulation of this problem. And so with this definition, we can state this the Spar-Andersen result. So the key word here is a universality. It's a universality result because it's something which holds for any model, any random walk, provided the increments are symmetric. So by symmetric, I mean that the distribution of x is the same as minus x. So we can take a Gaussian distribution, we can take a Cauchy distribution, uniform on some symmetric intervals. So many examples have symmetric distributions. And I also assume that we have no atom. Okay, so it's a kind of continuous or with density distribution. And the result is that this persistence probability, I mean the one I was mentioning before, doesn't depend, so is universal, doesn't depend on the distribution. And there is a very simple and combinatorial formula. So just take the central binomial coefficient 2 and n, and by some normalization, 1 divided by 4 to the n. And this gives this persistence probability. So it's a very surprising result the first time you can see it, because I mean, it's striking to see that it's just universal. It doesn't depend on the distribution. So of course, in probability theory, we have many universality results. It's something that we like in probability to be able to find universality. And maybe the most famous one is the central limit theorem. But the point is that for the central limit theorem, it's when n goes to infinity. And in this statement, it's for any fixed n. So from this point of view, it's a bit stronger because it's really something which happens all along the trajectory, not only when n goes to infinity. And if you want to compute the asymptotics of this quantity, I mean, it's very easy to use a Stirling formula, and you will get this 1 over square root of n as an equivalent when n goes to infinity. So I will not give the proof of this result, but maybe I can give one key idea in one proof. Sorry. So this is this beautiful identity between two power series. So on the left, I just have the generating function of the persistence probability. So we just add this variable z and power n, and we form the series. And on the right, we have the exponential of some power series. And what is nice in this identity is that if you look on the left, to be able to compute this probability, you need to look at the trajectory between time 0 and time n. I mean, to have a complete understanding, observation of the trajectory. And what is nice on the right is that you just need to look at what happens at time n. So it's much simpler to compute this probability. But of course, we have this exponential function which mixes a bit the things here.
Excuse me, Kilian.
Yeah, sure. Yeah.
What is the position of your particle at time 0?
Yeah, excuse me. In fact, it's 0.
Okay, it's 0. Yeah, this is what I must. Yeah, okay.
Yeah,
it's
excuse
okay.
me. No, I forgot to tell you. Sorry. Yeah, and so excuse me, and to explain how from this to deduce this Spar-Andersen theorem, so maybe it's obvious to all of you, but I just explain in 1 minute. If we have a symmetric distribution, of course, it has to be 1/2 here. And because we have this n here, if you put 1/2, you can recognize the series. So it will be -1/2 of logarithm of 1 minus z. So sorry, I don't have any thing to write. And the point is that if you simplify, because we have some exponential and some logarithm, you will get 1 over square root of 1 minus z. And if now you have this power series, we can just compute the coefficient in this power series, the coefficient of z to the n, and you get this nice and beautiful binomial coefficient. So really, the Spar-Andersen result, if you have this identity between two power series, it's an obvious consequence of this identity. But in fact, there are plenty of proofs. I would say that no one is very simple. I mean, it's really something deep on the random walk. Okay.
And so you have no condition about the moments of xi must be finite or not? The moments of xi.
Sorry. No, there is no condition. No condition. Yeah, good remark. Okay, so I mean, for the random walk, it's already solved. And what we did with my colleagues is to find another class of model, a bit more general, for which Spar-Andersen results wasn't known. And so it's exactly this class of model which I will now introduce. So it's called autoregressive processes, or sometimes AR for autoregressive. So it's a very classical model in statistics and also in probability. And there is this recursive definition. So here, it's a bit the increments of the random walk, that, something which is IID. And to define my process, it's a recursive definition. To define A at time n, I need to observe my process at time n-1 up to n-p. So p is the length of the past of my process. And then we have some either random variables or just parameters, which modify a bit the definition. So it's a general definition, which has a lot of applications in statistics. And in our paper, we just looked at a very simple version of it, namely to take p equal 1, I mean the simplest possible past, so p equal 1, and to take theta to be just a parameter. So theta is a fixed parameter, and we have this absolutely simple formulation for this autoregressive process. So it's called AR1, and the one because of the time of the past of length 1. So a very important observation is that if you take theta to be 1, you will get the classical random walk. So it's nice to have one parameter theta because it's exactly what we call a one parameter generalization of random walks. And there is a small connection here with random polynomials, because if we expand this definition, you will get that A of n is in fact a polynomial in theta, like this. And in front of theta n-1 and -2, you just have random variables. So it's just a random polynomial by definition. Okay, so I will not comment for now this last part of the slide. Maybe I will come to that later. And also maybe I can say that if you take theta to be 0, it's also something which is obvious, because in that case we forget about this term, and A of n is just equal to x of n, which is IID. So it's a kind of a white noise if you want. So theta equal 1 and theta equal 0, it's something already known and already solved. And we want to have this one parameter variation of the model. And now I can formulate the main question. So we have this autoregressive process A of n, and we can define the persistence event, which is that this process is positive or non-negative at time 1 up to time n. And now it has to depend on n and also on this parameter theta. So it's a family of functions of theta. And the questions are the following. Is it possible to have a Spar-Andersen formula in this case? If not, can we at least say something asymptotic when n goes to infinity? And maybe we can also solve for some particular case explicitly the model. And we will also try to think about symmetries in this variable theta. So for example, this function, maybe it will satisfy kind of equations in the variable theta. And I was mentioning that for theta equal 0 and theta equal 1, we already know how to solve the model. So we'll use this to understand some properties of the model. Okay, so do you have any question? Is somehow the model clear and the questions clear?
Yes, about the last line. What about 2 and 3 and 5? Do you jump from 1 to plus infinity?
No, I mean, yeah, it was not a very good idea to mention this. What I wanted to say here is that maybe it will become clear later, but just forget about infinity. I just wanted to say that if you take a theta to be plus infinity, somehow it becomes a degenerate. Yeah, I mean it's not clear. Sorry.
What about value 2 or 3 or 7?
Or maybe we can discuss later about this because I'm going to present some examples. But a priori, I mean, even if it's integer, it will not be anything specific for us. But good question. Okay, so this is the first result, which is quite simple. So the first one is simple, and then I will elaborate a bit about other things. Okay, so maybe you can take a look at this identity here. It's a relation between my persistence probability, let's say pk of theta, and Pn minus k, or pk, of 1 over theta. So a priori, theta can be any parameter, for example, 1/2. In this case, 1 over theta is 2. And so what we do here in this slide is to relate the persistence for theta to the persistence for 1 over theta. Maybe, I mean, if you take the sum of this identity here, you will get this kind of identity, which is maybe a bit simpler to look at. And what it says that if by chance you know this series here, so the series of the persistence at theta, you will be able to deduce the series of the persistence at 1 over theta because there is this relation.
But here theta is not random, it's deterministic.
No, theta is not random.
Okay.
I mean, of course, it would be an interesting model to look at theta random, but we started by something easier. Sorry. I don't know if there is a version. I mean, if theta was random, we could just somehow take the expectation of this, but okay. Anyway, so before giving the proof of this, maybe I can explain how to deduce from this Spar-Andersen theorem. If you take theta equal 1, it's nice because this is a fixed point of this transformation theta gives 1 over theta. And in this way, you will get the square of this series evaluated at theta equal 1, which is 1 over 1 minus z. And then taking the square root, you will get again this 1 over square root of 1 minus z. And this is this series. If you extract the coefficients, you get the binomial coefficient 2 and n. Okay? So it's just a simple proof of Spar-Andersen theorem, but it gives much more because it explains that finally there is a kind of duality of relation between the persistence at theta and the persistence at 1 over theta. Okay? And the proof is in fact quite simple. Look maybe at this picture here. So it's one example of autoregressive process. And what we do is that we split the path into two subpaths, and we split according to the location of the maximum or the minimum. Let's say the maximum. So this is the maximum here. And maybe you can imagine that if you look at the persistence probability, but now viewed from the maximum, you will get somehow two independent parts of the path, and you will get then a product of two persistence events. And somehow, I mean, this identity just is equivalent to say that we will reach the maximum at some points. We don't know where, maybe time 1, time 2, time n. And then we are going to have independence of the two parts, and each part gives some persistence event. So it's a very classical proof in probability and in random walks theory. Okay.
Sorry, this plot is the plot of what? This plot.
Sorry?
This plot that you have here is the plot of what? Of the probability or what?
Yeah, so it will be the product of two probabilities of persistence probability. So let me just recall that by definition, this Pn of theta is a probability for the autoregressive process to be non-negative. Okay, so this result doesn't say doesn't give a way to compute pk of theta. It just says that if you're able to compute it, then it's obvious to deduce pk of 1 over theta, just a duality. So now this is the second result, which is in fact, exactly the same duality. Theta gives 1 over theta, but now when theta is negative. And it becomes a bit more complicated. So now this is this relation, or if you prefer the series, it's written here. So it says again that if you know what happens at theta, you can deduce what happens at 1 over theta, but the relation is a bit different. Now we have signs. You see there is a minus here, and this is not a 1 over 1 minus z, but just 1. So this result is much more complicated, and we don't have a simple proof as here, where we just had to split the trajectory at some random time. I mean, here we have a complicated computational proof, and we don't have any nice and beautiful probabilistic argument to prove this, but maybe you can have an idea on this problem. Anyway, as a conclusion of these 2 slides, what happens is that we have a central regime for theta between -1 and 1, and then we have this duality, which makes that if you know what happens between 0 and 1, you know what happens between 1 and infinity, and the same between -1 and 0. You get this part in green between -infinity and -1. Okay, so as a conclusion, we just want to understand what happens for theta between -1 and 1, and then we are going to have this universality result about transferring the parameter theta to 1 over theta. So this is why now we are just going to be interested in this regime where theta is between -1 and 1, because it's all we have to say. So I guess it was somehow clear to you that we have a very simple formula for the probability Pn of theta, because we have a density, and this density involves the variables x1 to xn, and so we can just integrate the product density because we have independence of the variables. And so we get that Pn of theta is equal to some n-fold integral, and here we put the product density, and then we write all the conditions of the persistence events. So we want to be positive at time 1, positive at time 2, etc. So a very direct formula for the persistence probability. So in fact, it's related to, it's exactly a volume of something, right? It's a volume of some polytope. I will explain maybe a bit later what happened here. And of course, we cannot hope really computing this kind of integral, because what do we need about the density f? So somehow we want to integrate the density f, and also we are going to evaluate the density at sums, for example, x2 plus theta x1. And I mean, it's why here I have written that it would be very nice if we had additional formula. For example, if you have the exponential function, it's easy to compute the exponential of a sum because we have a product formula. But in general, if you have a complicated density like a Gaussian density, it will not be possible to compute this Pn of theta. So we have to think to find a way to find some idea. And in this talk, what we did is that we tried to find the simplest possible formula density, because we wanted to compute this probability. And in our opinion, the simplest possible formula was to take f to be 1, just so a uniform distribution over, let's say, -1, 1, but it's not important. It can be -2, 2, or any kind of, let's say, symmetric interval. So something maybe I should have mentioned is that if you take the exponential function, there is some paper by Laralde, so a physicist, who computed, in fact, this probability. So it was possible because of the nice properties of the exponential function. So somehow, what I'm going to present now is a second work. So there was something about exponential, and we did something about the uniform distribution. Okay, So first, we can compute, just to see a bit what is going on, we can compute a few probabilities. So P1 of theta, I mean, it's totally obvious because it's a probability that one variable, which is symmetric, is positive. And so, of course, it's 1/2. So nothing to say about this. It's a bit more interesting to compute this one here. So now I have two conditions. The first variable should be positive, and the second one should be a non-negative as well. So it's a double integral. And so x1 has to be positive, so everything is okay. And what is interesting is that here, in this in the inner integral, I have two conditions. So x2 is a uniform in -1, 1, so it has to be between -1 and 1. And also we have this condition which should be true, and which says that x2 should be bigger than minus theta x1. And this is why we have two conditions here, okay? One condition because of the distribution, another condition because of the conditions of my persistence event. And finally, all the complexity of the problem comes from here because we have a complicated bounds in these integrals. And you know, if you take theta, for example, to be close to 0, then it's a good case because we can simplify this. If you take theta to be close to 0, the infimum will be always theta x1, right? But if you take theta to be very big, then somehow we have to compute different cases and sub-cases, so it becomes quite complicated. So let's say in this slide, I take theta close to 0 to have a simple bounds in the integral. And in this case, I just make the computation, and I get theta plus 2 divided by some, just some renormalization factor. And the same for P3, we get this combinatorial polynomial in the numerator, and we also have a normalization. And to be honest, so it was exactly the beginning of the story. And Thomas Simon was working on this and just checked a few polynomials. And then for some reason, he knew this polynomial and was able to make a conjecture that this persistent probability should be related to a family of polynomials, which are exactly this one. So this is at the time the conjecture. Now this is a theorem which says that Pn of theta, if you have the good normalization, it's something called a Mallows-Riordan polynomial. So this is something defined in combinatorics. So I will exactly explain what it is. It's related to trees. And okay, so again, it's thanks to Thomas Simon, who was clever enough to know this polynomial by heart.
Excuse me.
Yeah.
Tom is a good friend of mine and of other people. He knows many other polynomials, and he knows them well. Okay, you continue. Okay.
No, he's impressive, definitely. Okay, so in the slide before, I said that we had to assume that theta is close to 0, just to simplify a bit the integrals, right? And in fact, it's important because in the theorem, we have a condition on theta. And indeed, theta should be not too close to 0, but somehow close to 0, and more precisely between -1 and 1/2. And so at the end of the day, we have this picture here. If you take the uniform distribution on -1, 1, we know how to compute the persistence probability for theta between -1 and 1/2. And now remember that we had this duality theta gives 1 over theta, so we can move to the negative axis. But the point is that because we don't have this red interval -1, 1/2, 1, sorry, we also miss the symmetric interval after 1 over theta, 1, 2, and then between 2 and infinity, we know what happens. And so in this work, in this paper with Aline Bustan, Gerold Hassmayer, and Thomas Simon, we miss what happens between 1/2 and 2. It's still an open problem. So If you have some idea, again, it will be very welcome because we have no idea what is going on in this interval. We are not able to compute the persistent probabilities in this interval.
Why we cannot use the duality in 0, 1?
I mean, we can use it, but the point is that we have no explicit formula in this red interval. So the duality will be true, but we have no explicit formula. And somehow this theorem here gives some explicit formula between 0 and a half. Okay, but we miss the interval, the segment a half 1. Okay. So I have 5 minutes left. So maybe I can make a picture of what typically will be this persistence probability. So this is a graph of P5 of theta. So just forget about the pink curve. Just look at the brown one, so this one. So what is important in this picture is to take a look at the blue points, all the blue points here. So what happens is that there is a formula for the persistent probability for theta between -1 and a half. So this is this interval that you can see between the two blue points here. Okay. Between infinity, -infinity here, and 1, so we have the duality. So we know how to compute this. And then we're at a half. And what you can see here, in fact, in each very small interval, we have a new definition for the persistent probability. It's a kind of a piecewise defined function, but maybe we have 10 conditions for n equal to 5. And in each subinterval, we have a new definition for the persistent probability. And we have the connection with the Malus-Redon polynomial only in the central interval -1 a half. And this is why it's very hard a priori to understand what happens between a half and 2, because the more the bigger n will be, the more intervals you will have here, and we are going to have at the limit infinitely many different definitions for the persistent problem. So it's very a difficult problem. Anyway, maybe now I can define what is this Malus-Redon polynomial. So here you can see a paper by Malus and Redon, who introduced in 1967 this family of polynomials. So to define this, just take a look at this function. So if you take theta to be 1, it will be the very classical exponential function. And if you have this further parameter theta, it's called a deformation of the exponential function. But still, you can make a series expansion at z equals 0, and you get 1 plus z plus z squared over 2. And then we have some quantities depending on theta here. And because we have a 1 plus something, we can take the logarithm of the series, okay? And then you get a new series, and in this new series, a series in Z, and all the coefficients will depend on theta, and then you can just compute, you can prove that it will depend on theta, a half in a very simple way, because it will be theta -1 to the n -1, but there is also some mysterious polynomial appearing, and it can be taken as the definition of the Malus-Redon polynomials. Okay, so it's a bit computational, but it's some analytic definition. And what is very beautiful is that in this paper by Malus and Redon, they gave some combinatorial interpretation of this identity here. And I can explain how it works. So take a tree. You put the root here at 1, okay? So this is a fix. The root is at 1. And then we take a tree, and we just put labels on the trees. So here, between a 2 here and 8. So it's very classical to count how many trees, how many label trees we have, okay? it's given, I mean, it's called the Cayley formula. It's n to the n minus 1, where n is the number of leaves. Okay. And the Mallows and Riordan wanted to introduce a generalization, a refinement of this result. And it's, you know, you can see the title of the paper, it's related to inversion. So what is an inversion? You start from the root here, and then you go along all subtrees. And an inversion is if you see two labels which are not increasing. So for example, here it's okay because it's 1, 2, and 7, so everything is increasing. But here we have 1, 5, and now 4, or 1, 5, and 3. So in my example, I have two inversions. So Cayley formula, so the n to the power n minus 2. Now we can say that we are going to count how many trees we have with a fixed number of inversion. And this is exactly the definition of this Mallows-Riordan polynomials. So I don't know if I was clear or not, but there is a very direct combinatorial interpretations in terms of trees and inversion. So, I mean, of course, for us, we have no idea about this link, a direct link between this combinatorial interpretation and the formula for the percent probability. I'm just saying that this is the initial definition, and for us, it's something just a bit miraculous. Okay, so I see that I should somehow stop, so maybe I can just explain a very last thing.
You have 5 extra minutes if you need.
Okay, thank you. Let me just think a bit what is the most interesting thing to say. Okay, so maybe because I know that's the probability in the audience, I can explain a connection with probability. I mean, between Mallows-Riordan polynomials and some distribution in probability. It's about the log normal distribution. So by definition, you take a normal distribution, and then you take the exponential of the normal distribution, and it's called the log normal distribution. So you can see a few pictures here. And in probability, we have something called a cumulant generating function. It's when you take the logarithm of the expectation of E exponential of the variable. And my point is that imagine that for some reason you want to compute the cumulant of the log normal distribution. Why not?
No, 1 second. Kilian.
Yeah.
In fact, the generating exponential, the generating function does not exist. And so this means that the operation you show now, it is a little bit formal.
Yeah, no, excuse me. Yeah, you are
Okay.
totally right. Exactly.
Yeah, it's not so straightforward because I have done some work involving the log normal distribution, and we have to be very careful and to tell correctly what we do and why. Okay, you can continue. Sorry.
Yeah. No. So it's a very good remark. In fact, I mean, all of this is totally has no sense in the sense that if t is positive, everything diverges. Okay. It's just an equality between formal power series. Everything, I mean, not everything in my talk, but a lot of identities, in fact, were just formal identities and the equalities between formal power series. So it's totally true. So for example, if you take, I mean, you can see that because of the E to the power n squared, it will never be possible to compensate with just t to the n or n factorial. So this is somehow this is infinity is equal to infinity, but we can give a sense in the world of formal power series. But anyway, once we have this correct meaning of the identity, so we can give a sense to it, and then we see that it's exactly what I was mentioning before. We have a logarithm of a series. We have this t or z to the n, and here we have a theta to the power n minus 1 over 2, just n squared, which is basically the same. So I just wanted to say that if you want to compute this series, you will get the Mallows-Riordan polynomial again. So it's nice way to see again the connection with malus random polynomials. Okay, so maybe I will stop here. Pardon me?
Sorry. Thank you, Kilian, for this nice talk.
Thank you. Thank you.
Are there some questions, please?
Hello, Kilian. Yes. Can you go back to the last slides, page 16? Okay. Okay. Then the cumulative function has a signs for t negative at least.
Sorry?
The cumulative function has a sense, is well defined for t negative or negative t.
Yes.
And y is infinitely divisible, then you have probably a Bergson function here. A minus the log will be a Bergson function.
Yeah, so I don't have anything to answer. Yeah, I mean, so we explored a bit the connection between, I mean, not especially this identity, but all the persistent probabilities and special functions. But I cannot remember that we had something related to Bernstein function. So yeah, maybe
you certainly have that. There is many objects hidden in your talk which indicate the existence of infinite divisibility.
Yeah. So indeed, this we had some infinity divisibility results. Yeah.
And in the positive case for distribution on R plus, you'll find a lot of Bergson functions everywhere.
Mm-hmm. Yeah, maybe, yeah. So maybe we should discuss with them because I have no idea. But you are right. We did think a bit about this infinite divisibility properties. Yeah.
Actually, the first indication was on maybe on the slide 5.
Excuse me.
No, sorry. Can you go? Can you stop here? Then the last formula is due to Spar-Anderson, right?
Yeah.
It's very, very, very surprising formula. Huh?
Yeah, indeed.
Then, can you go to page 7, please?
Yeah, sure.
No, maybe I missed the page. This one. Yes,
pardon.
This one. Then, if you put z equals exponential minus u, you find a kind of factorization for the genetic kernel of all Bergson functions. Then I guess there is a lot of hidden infinite divisibility in your story.
Yeah. We can discuss more about, see if you want. Indeed, we have some statements. I have forgotten which ones, but we're able to prove that some distribution were infinitely divisible for sure. Yeah. I think just the first time that's maybe just this variable that's the first time that you become negative. So what I call the tau. Maybe this one or yeah. Maybe we can discuss later if you want.
Okay.
Other questions, please? I have a general question about the trees. N to the power n minus 2. Please, if you can go to the slide where. Okay, this is any kind of trees or some special trees here. And
no, it's I mean it's just a label trees of cardinality n if you want, but no other assumption. Okay.
Okay, no condition about the number of descendant of any node here. We can have 1, 0.
No.
Okay.
No, it's a very just counting any kind of trees of
any kind of level trees.
Yeah.
Okay. Okay. Other questions, please? Are there other questions? If not, we have to thank again Kilian for this nice talk.
Thank you. Thank you.
Thank you to the public, and see you next webinar. Thank you.
Is there a talk next week?
Sorry?
Do you have a talk next week or in 2
No,
weeks?
not sure next week,
Okay.
but after 3 weeks.
Okay.
After 2 weeks, sorry. Merci beaucoup, Kilian.
Ouais, merci. À bientôt. See you.